event today. So thanks for that, Ben. Ben. And he's a local. So he's also our first local. He's with us here from Calgary. Ben is a software and machine learning engineer at Viewpoint Investment. And I'm just going to read a little bit about your bio, Ben. Like many Albertans, Ben has transitioned from oil and gas engineering to the technology industry. And currently he's in charge of building out the software and AI capabilities of a startup investment management firm. Again, it's Viewpoint Investment. And as co-founder of the YYC Data Society, he's passionate about building out Calgary's and Alberta's local technology economy. So excited to have you here, Ben. In this session, Ben is going to guide us in exploring how we can use the intuitive techniques of Bayesian statistics to understand our data and tell its story. Did I pronounce that right, Ben? Is it Bayesian?
I say Bayesian. Some people say Bayesian. Yeah, I'm not really sure. I mostly see it written. So there's not a whole. There's not many Bayesians out there is the right thing. So I think however you want to pronounce it is fine by me.
Awesome. I feel like we can make some good jokes out of that word. But before that, we're going to pass it over to you to talk to us about Bayesian statistics and how to tell our data story.
Awesome. So you got 30 minutes or so to think up good jokes then.
Awesome.
Cool. So yeah, welcome everybody, and thanks for tuning in to this session of DevFest Alberta, where, as mentioned, we're going to spend a bit of time together learning how to speak the language of our data. So, like mentioned, my name's Ben, and I run the software engineering and data science arm of Viewpoint Investment Partners, which is a quantitative investment management company here in Calgary. As mentioned, also one of the co-founders of the YYC Data Society, which is a not-for-profit that aims to bring AI literacy and investment into Calgary and Alberta. So, we're going to talk about some tools and techniques, specifically that are built around allowing you to combine your human intelligence with the power of machine intelligence and modern computing that's going to teach you how to reach some insights that make sense in a way that humans can understand, but can also be verified empirically with machine learning. So why do we need to even bring human intelligence into the picture? I mean, isn't AI kind of the new intelligence? So I specifically work in financial markets, and working in financial markets, I'm surrounded by data that is determined to lie to you. So it feels like the data is almost malicious in its desire for you to overfit it, to mine out spurious correlations, and to be fooled by illusions of pattern amidst the noise. And so what does it mean to have data that tries to lie to you? Well, data that's going to lie to you is going to often have a very low signal-to-noise ratio, so lots of randomness amidst what's meaningful. The data is often going to be smaller in size or inconsistent, and the data may change its behavior over time. When you kind of have all of these together, what you're left with is an unkind learning environment. Now, most modern machine learning systems, they're actually not that well suited for this type of unkind learning environment. For example, what that means is like a computer vision algorithm, it expects a picture of a cat to always be a cat. You don't have the picture of the cat, and half the population sometimes says that it's a picture of a dog. You wouldn't have people disagree and say that, these two pictures of cats and dogs are actually the same picture, right? You expect to have the same input data lead to the same output time after time. Also, thanks to Kyle from before for letting me know that you can always include a cat in your presentation. I didn't know that, but thankfully I do have one, potentially two pictures of cats right here, depending on your perspective. So when we're dealing with chaotic data, right? What can we do in that scenario? Well, obviously, we want to have a solution that helps us to differentiate between meaningful structure and randomness. Now, one of the greatest tools that we have in pursuit of discovering the structure of the world is the scientific method. We don't need to go through the whole scientific method together now, but really the way that it works is that you generate a hypothesis, which is a story about how the world works. You combine that with your existing theory and some of the evidence of the data that you've gathered. You perform inference and analysis, and you come up with an updated worldview. Right, but note that we have a hypothesis, we gather evidence, and we push it through an inference system. And another great strength of the scientific method is that it allows for uncertainty. Right, we don't assume that just because something worked the first time, it's now a new law. Every time that we test out a hypothesis, a new theory, we strengthen our belief in it. And if the data changes or if our results change, we update our beliefs as that change occurs. You may be wondering, like, Ben, why are you talking about the scientific method right now? What does this have to do with data and AI? Well, really, when you're faced with data which likes to misbehave, we can actually select machine learning strategies which integrate with the scientific method and help us to bring our human expertise into the equation. So how do we go about putting the science into data science? There's definitely multiple ways of doing it, but one of my favorite is what's called Bayesian inference and Bayesian statistics. So in this case, we map a hypothesis to what we would call a data generation process or a data generation story. So we create, that becomes our hypothesis, we take a look at our data, and we use our existing knowledge about how the world works to set up our prior beliefs. Now we combine all of these things into some type of inference engine, which in today's session, it's going to be Markov Chain Monte Carlo, but we're not going to get into the weeds of how it works. Effectively, it's just a black box process for turning our hypothesis and our data into an updated set of beliefs. Now, for the Bayesian side of things, the only thing that you really need to know, I guess, is its general perspective of the world. And the general Bayesian's perspective is actually best summarized by famous economist John Maynard Keynes when he famously quipped, when the facts change, I change my mind. What do you do, sir? Right? The Bayesian worldview is all about updating your beliefs as the facts and as your data change. So we're going to spend today's session by understanding by doing as opposed to telling for the most part. So let's kind of get started. Let's set the stage. So let's imagine that you're the lead data scientist in a fast-growing startup. Right? Your company's made a sizable investment in optimizing your marketing campaign in order to drive additional traffic to your website. And so we've got this red line in the chart that shows when we initiated the new marketing strategy. And now we're a year down the road, and the CEO is asking you, the chief data scientist, if the marketing campaign was successful. Right? Now, what you tell the CEO is going to determine if you renew the marketing initiative, which is going to cost 3/4 of the yearly marketing budget. Right? So this is an important decision to be made. Naturally, I would imagine the first thing that you would do is make the plot that we show here. So we have our daily website traffic, the number of visitors to the website, plotted over time. And we know that on day 400, we launched our new marketing campaign. The question that we're trying to answer is, did our growth rate, did the rate of growth of our website change over time? Now, think through, spend a bit of time thinking about how you actually might go about approaching this problem. There's obviously many ways to skin a cat in tech, and there's multiple approaches. But as you're kind of thinking through it in your own head, keep in mind that you're going to have to testify in front of the CEO on a crucial decision that could change the fate of the business. So we want to be really confident in our answers. Now, before, I'm sure that you guys are all itching for me to tell you how we're going to go about solving this problem, but before we get too far ahead of ourselves, we actually want to spend a bit of time understanding what it means to tell the data's story. Like, how does data have a story? So, broadly speaking, we can categorize most, if not all, machine learning algorithms into two categories: discriminative models and generative models. So let's imagine that we're trying to determine the difference between hand-drawn digits, right? We want to decide, we want to take a scan of an image and figure out if somebody drew a 0 or if they drew a 1. Now, a discriminative model is just going to try and learn the boundaries between the classes. They only care about learning the differences between zeros and ones, right? So they're going to map that data onto a projection and try and draw some type of boundary, some type of line in between the two classes. Now, a generative model, on the other hand, it's trying to learn what the underlying probability distribution or the underlying data generation process, which actually creates a 0 or a 1. So it's trying to figure out like what makes a 0 a 0 or what makes a 1 a 1. Whenever it's trying to classify new predictions, it basically takes a look at the new data point and says, how much does this look like a 0 that I've seen before? Or how much does this look like a 1 that I've seen before? So in terms of these two paradigms, one of them, discriminative models, they only look at the differences between classes, and generative models are able to actually model how the data comes about. Yeah, let's move on from that for now. So with that in mind, that a generative model is looking to tell the story of how the data actually comes about, we can kind of come back to the question that we've been asked by our CEO, which is, did our marketing strategy cause some type of change in web traffic growth? Now, we also are wondering, like, what does it mean to bring the human intelligence into this? So with our human intelligence, I mean, we can build out a mental story, a mental idea of what happened, right? We imagine that, initially we had some sort of initial rate of growth in the website traffic. It was growing by, a percent or two every single day.
And once we've adopted our new marketing strategy, the rate of growth may have changed. We expect new people to come to our website more frequently. Now, as we think through that mental model, what we've actually done is we've described a story. We've described a hypothesis for how our data may have actually come about. What our task is to figure out how to translate that story into the language of statistics and mathematics. And once we've been able to do that, we can, plug that story, plug that hypothesis into our magical inference machine, which in this case is Markov Chain Monte Carlo simulations. And we're going to be using a Python library, PyMC3 for this. And let's actually dig into what that looks like. All right, so we've got a Google, so I've done this demo in Google Collaboratory, so everybody, I'll definitely share the links for the demos with this, with the group afterwards. And so through this notebook, what we're going to do is we're going to simulate some possible website traffic data. We're actually going to create the data set that we saw before of that website traffic changing over time. And then I'm going to show how we can use MCMC, Markov Chain Monte Carlo, to show how we can actually make those hypotheses about our data generation story and then gather some insights. So first step, we just have to update some libraries that aren't in the default Google Collaboratory runtime. And if anyone hasn't used Google Colab, it's quite nice for quickly putting together and sharing code with people. So it's just a nice notebook environment. we got to set up our imports. If you're not familiar with Python, I would say don't worry about it. For those of you who are familiar, PyMC3 is the main library that we're using, and it's built on top of Theano, which is a mathematical computing library that was kind of the precursor to TensorFlow and PyTorch. Since then, it's kind of stepped down as they stopped development on it and let PyTorch and TensorFlow kind of take over, but it's one of the originals and one of the greats. So first thing we got to do is we've got to start setting up our sample data. So we're going to actually just generate some hypothetical website traffic data to simulate our environment. So we're going to create 1,000 days worth of data at t=0, so at the beginning of our data set. We're going to assume that we've got about 10 visitors hitting our website organically per day. We're also going to simulate that originally our website traffic is growing at 1% per day, and at time equals 400, we're going to say that this is when we initialize our marketing campaign, and the growth rate actually jumps from 1% per day to 1.5% per day. So a 50% increase in our growth rate, which is quite nice. So we kind of set up our parameters over here. We're going to set up our rates of users. So we start off with 10 users per day. We say it's growing by 1% for the first 400 days, and then it grows by 1.5%. This data is controlling, this is controlling how many visitors we expect to see per day. So we're allowing it to grow over time. We combine our two periods together, and what we're left with is this array, which tells us how many visitors we expect to see on the website on that given day. Now, we actually have to, of course, simulate that. So what we do is we sample from a Poisson distribution. Those of you who aren't familiar with stats or don't remember it or don't care, you can just imagine. The only thing that's important to know is that a Poisson distribution, it describes events that occur over time. So we're interested in the number of website visits in a day, which is modeled by a Poisson distribution. So we can go about and plot. We can plot what that winds up looking like, right? Now you can say, okay, maybe this looks like there was an increase, maybe not, but it's kind of, I don't know. I think it's kind of hard to tell. It doesn't look especially clear to me at the beginning. So what we're going to do next is we're going to use our PyMC3, our Markov Chain Monte Carlo simulation library, to express our human intuition for what happened, and we're going to test that hypothesis on this data that we've observed. So how do we do that? So the first thing that we have to do is we're going to express our data generation story in human terms. So what that is that, in human terms, our rate of initial website traffic started at some initial value. We don't know what it is, right? We assume that the traffic was growing at some constant rate at the beginning. And then at some point in time, probably day number 400, our growth rate actually changed and went from being, a lower growth rate to a higher growth rate of traffic. This is our hypothesis, our story. Now, in order to test that out, in order for a computer to test to see whether or not our hypothesis was accurate, we need to express that in the language of math. For those of you who haven't been to a math class and have no intent of returning, you don't have to worry about it. But this is what it looks like to translate the human language into mathematical language, right? So we start off with our theta naught, which is our initial the initial number of users that we expect there to be per day. We've got our growth rate for time period A, and then our growth rate for time period B. At some time tau, there's a change point, and so our growth rate is If our time period is less than our change point, we have our slow growth. Otherwise, we've got our higher growth rate. And we just combine that together to express our expected number of views per day in terms of some nice little math function. And what we get with is we now have a way that says, okay, our expected number of views is sampled from this Poisson distribution at a rate of theta I. Now, again, for those of you who aren't familiar with the notation, not a big deal. The important thing is kind of like how nicely that this notation of translating from human language to math language and then to Python language, it maps almost kind of one-to-one. So we see that we've got our data generation process specified in math terms, and we move down to specifying it in Python terms. So we're creating a new model. A model is the container for our data generation process. And we say that, okay, like we're initially starting off with a some number of views per day. We're not quite sure what it's going to be, so we're going to guess that it's going to be some range of values. Don't worry about that. We're just using an exponential distribution for this. It's not important. And we're going to expect that there's going to be, the long-term, we're going to expect to see, about like the average number of views per day. We then we define our two growth periods, our initial growth period and our growth period B, so that maps to these three lines right here. We define out that there's going to be some switch point where we change from our original growth rate to our second growth rate. So we're just using a switch to tell you if we're less than, if our switch point is below our index, then we use growth rate 0, otherwise growth rate 1. And then we just calculate our growth rate for that day. This is just this line right here where we're saying our expected growth rate is our initial rate plus our total growth received up to that point in time. And finally, we say, okay, our expected number of views is sampled from a Poisson distribution that comes from these comes from this number, and we punch in the actual data that we saw. So in just 7 or 8 lines of code, we've translated our human hypothesis for how the data is created, translated it into the language of math, and then put it into the language of statistics for our model to consume. So we can also visualize what that looks like. So we've got our initial growth rate, our secondary growth rate, we have our initial number of viewers that we expect per day, and we have our change point. Those all kind of go into this little equation that determines how many expected viewers we have on a given day, and that is used to determine, is drawn from a Poisson distribution, which allows us to express the uncertainty. Right here, I redefined the model just in a more efficient format. It's the same thing, it just helps with some of the computational complexity. And what we're going to do is we're then going to basically click what I call the magic inference button, which is, PM pi MC3 dot sample. So we use our model that we've defined above as our context. And what's happening here is that our model is going to use our specified data generation process. So it's going to use this model, this view of the world that we've given it, and it's going to simulate 2,000 different possibilities of how that data could have been generated. So we're going to get a set of parameters, which actually 2,000 sets of parameters, which tell us, okay, if this hypothesis that you've given me, if this data generation story that you've given me is correct, then what are the possible values of your parameters? What are the specific details that would lead this to be true? So we do that. I don't run this here because it takes a little bit of time. And then we can come down and we can take, let's just look at it over here. And so we take a look at all of the, our trace object, this guy, he's got 2,000 items and he's got 2,000 different options of basically what our parameters likely could have been in order to have seen the data that we saw. So we see that, at the estimate for how many views you'd expect to see every day at the beginning, you can see that, okay, it's actually estimating about 9.75. We know that the true rate is, 10 views per day. And it's saying, okay, well, it looks like, you've got between 9.5 to 10 views per day, that this is what, at the start, right? So at the beginning of the data. We can also plot out what it thinks the growth rate was, both before at the initial beginning period of time and after our switch. So this is the distribution of possible growth rates that we have at the beginning, this blue guy right here. And this is showing us that it expects actually that our, it's correctly identified that it thinks that our growth rate was probably about 1% per year, or 1% per day at the beginning of time before we have our switch rate. And note that this is a distribution, so it's saying that while it's most likely it was about 1%, it also could have been 1.1% or 0.9% growth per day. And then it would come through and we're able to also model what the growth rate of views per day was after the switch point, after our marketing campaign. And we see, wow, okay, most likely our growth rate after the switch point was about 1.5% per day. Could have been 1.4%, 1.6%. But what we are very confident in is that there was a marked increase, an increase of about 50% after we implemented this marketing campaign. So if you're imagining that you're coming to tell your CEO whether or not this marketing campaign was successful, what we're able to do is we've created a story in our heads of how things work. And under that story, we see that, okay, wow, it looks like there's about a 50% increase in our traffic growth after we implemented this new marketing campaign, which sounds good to me. And we can finally take a look at plotting what our actual rate was, because we generated this data ourselves. We can take a look at plotting the actual rate versus what our simulation engine thinks our expected rate was. So we've got this black line that shows, hey, at time t equals 400, there's a bit of a kink, and our growth rate changes and gets a bit steeper. And we've got these red lines, which are what the model thinks the possible range of parameters could have been. And here we also see that kink. And so we would at this point, I would come back to the CEO and tell him, hey, actually, I do think that we have, I do think that this was a worthwhile investment. Well, that's my reminder for my demo slide. Now, this is just one aspect of ways that we can use MCMC to simulate our possible scenarios. So what are some other things that we're able to do with this? Well, since what we've done is we're specifying a generative model, a model that actually allows us to create examples, right? Remember, in that past demo, the way that we got an idea of what happened was by simulating 2,000 different possibilities and checking to see how reasonable those possibilities were. Since we're able to simulate possibilities, we can actually use that to simulate what might happen in the future. So we can quickly take an example from my home environment of financial markets. So I assume that many of you are aware. If you weren't, you're learning now. But financial markets were very volatile during the COVID-19 lockdown and economic shutdown, right? Markets started to crash and they became very volatile. They jumped around quite a lot. Now, as things begin to stabilize, one of the things that I have to answer in my firm is, are things calm now? Are we actually able to relax? And so for time, I'm not going to go through this next demo, but what we're able to do is we're able to, in the same way that we did last time, we develop a data generation process, we develop a story of how the volatility, how the uncertainty and the randomness in financial markets evolves over time, and we use MCMC to figure out what sorts of parameters make that story the most reasonable. We then use the results of figuring out the details of how that story comes about in order to simulate some future possibilities. And you can see, so the results of the fit of how volatility evolves over time is kind of given in this top chart. So when the green piece gets higher, that means that the model has expected our volatility to increase, and you can imagine it sees that volatility is most increases over the COVID crisis, over this little random huge spike in returns over here in early 2020. And so we go through we fit everything, and then we use the results in order to simulate new possibilities. And what we see is that if the current environment that allowed the COVID-19 crisis to kind of happen, if that current environment continued, well, we're actually, most likely we're going to see some positive returns and markets are going to continue to be strong, but there's a lot of lingering instability, and we may be, primed for another drawdown, which is as about severe as the past one. Markets could continue to rise up on news of the vaccine, and so there's still a lot of uncertainty in financial markets. And coming back to my bosses and my team, I have to tell them that while things are looking generally positive, there's still a lot of uncertainty in these markets, and so we should exercise some caution. So anyone who wants to go through the ins and outs of how to actually do that is welcome to pull these slides afterwards, but I think in the interest of time, I'm going to skip over that. So there's another option that people can use for Bayesian some of these things, and the scientific realm also can benefit from some of these tools and techniques and ways to translate a data story into meaningful results. So in this next example, what we're going to look at is we're going to look at some dynamics of a predator and prey relationship. So we're going to look at some data from the Hudson's Bay Company up in the Arctic and trappers back from the 1900s, who were looking at the relationship between the population of Arctic hares and the population of lynxes, which are the hare's primary predator. And so what we're going to do is we're actually going to use a well-known ordinary differential equation to specify the dynamics, which is our hypothesis of how the relationship between predator and prey actually goes about. What we want to do is we want to estimate what the details of those parameters are. We've specified the structure, but we want to estimate what the actual values themselves are by simulating some possibilities and checking to see what looks the best. So coming into this data, again, this is another one that we've done using Google Collaboratory and is available for anyone to come through and play around it. So the first thing that we've got to do is we're going to read our data for lynx and hares, for predator and prey populations. So we've plotted it right here. We've got the hares in this orange, and we have the lynx population in blue. You can see, as you might expect, as the population of the lynxes, predators rises, it kind of hits this instability point, and the population of hares drops off, and as there's less food for the lynx, their population falls back down, which allows the hares to rebound, and so on and so forth. So this is a phenomenon that had been noticed in ecological studies previously, and a couple of scientists came up with a differential equation that kind of explains how this might go about. So we're going to, this is called the Lotka-Volterra equation. It's not super important, but basically what it's going to do is it's going to describe the growth rate of our predator and prey populations over time. And we're able to take this expression, this expression for how the mechanics of our system evolve, and use that to simulate what future possibilities might be. So all we have to do is we specify our function for how things evolve, and we specify how to simulate possibilities, which is right here, which just uses SciPy's scientific Python computing's ordinary differential equation integrator to just simulate. If you give it in some parameters, it'll simulate the how the population would have evolved. So we're going to create just like last time, we're going to create a PyMC3 model. And in this time, what we're interested in finding is these 4 parameters. We're interested in finding alpha, beta, gamma, delta. If it helps, alpha is the natural growth rate of hares. Beta is the natural dying rate of hares. Gamma is something like how many hares a lynx has to eat in order to create a new baby, and delta is like the natural dying rate of the lynxes. And so we want to estimate these 4 parameters. We plug them all into a simulator. We say, hey, magic inference engine, go about, and we're going to tell you how the data gets generated, but we don't know what the details are, right? You go through, you run a whole bunch of simulations and compare how closely those simulations look to the actual data that we observed. And this one I'm also not running because it takes a long time. And we can come through and we can see what the model has come back with and what it thinks our parameter estimates are. And so it's estimated that so it's come through, it's fit very well, and it's telling us that, for example, our alpha parameter is probably somewhere between 0.44 and 0.63. And this is actually quite in line with academic results, just in the interest of time, skipping over. And you can see that there's a relationship that, our model has actually created these simulations to fit the dynamic based off of what we've given it. It's not perfect. You can see that it kind of, it fails to account for, it comes down a little bit too low. But in general, our simulation engine has figured out what our parameters should be such that the results are pretty close to what we would have expected. And so just in the interest of time, we're going to skip over these conclusions. I'll quickly run through the conclusions. I mean, the reality is that all models are approximations, and that the real world, it's messy and it's chaotic. Now, useful models help us to answer questions about, what does it mean if I see X, or what happens if Y changes? We can use generative models to help us understand how our data came to be, and we can use Bayesian methods to help our models understand how our data came to be. So combining both together through something like MCMC allows us to create some really interesting and unique perspectives. This final example down here below is actually some German scientists created up-to-date and always changing estimates of how COVID was spreading through Germany using, techniques that would allow for them to change their forecasts in real time as new data was made available and as the government took interventions. This type of technique is not available to most machine learning algorithms that require a large amount of historical data. So they can't deal well with unprecedented times, whereas these researchers used PyMC3 to create, up-to-date and reasonable estimates by combining their prior knowledge, their human intelligence, and combining it with a powerful ML technique to produce awesome and final great results. So that's it for me. I can't really get on stage without having a couple of quick shameless plugs. So if you guys are interested in data science and data engineering and you want to learn more, we're hosting a 2-day data science conference in March of 2021 called the YYC DataCon. Anyone is able to register, and tickets will be on sale here pretty soon. We're going to have 20 or 30 speakers from across Alberta. And you can also look up LinkedIn and follow us on LinkedIn, the YYC Data Society, to keep it up to date with all sorts of events that are going on. So I think with that, I will stop the presentation and open it up for any questions if I have time. Yes, I will post the link to register.
Awesome. Thanks, Ben. I need you to join my marketing team. That was amazing. So I'm just going to open it up because we haven't gotten many questions into the chat room. So does anybody have a question? I know Roy and maybe Vanya said that they would have questions. Hello.
Well, if nobody else wants to ask anything,
not at the moment.
Well, in general, these kinds of simulation techniques, your assumption would be that the model that you have is perfect, but what if that's not the case? Like in the animal predator case, what if there are some correlations, like once 100 lynx dies, the population moves to a separate location? It's some inbuilt intelligence that you did not know before you created the model. Or like in finance domain, what if like the decrease in price of GPUs actually boosts the sale of Windows computers more than Mac? Like there are so many correlations. Like how would you deal with those kind of things in simulating and doing these kind of techniques?
Yeah, that's an excellent question. So at the end of that presentation, like I said, all models are approximations. There's never any way that you're going to be able to perfectly model how reality works. No techniques that we have currently available are going to allow us to do that. So all models are approximations. Some are just more useful than others. So in this case, we're generating these hypotheses, this data generation process, and then testing to see how reasonable it is. So there's I believe it's Andrew Gelman who has a quote that's basically, if you're trying to fit an MC model and you're having inference problems, I didn't get into it it's a bit too technical for this talk, but there's lots of diagnostics and ways that you can check to see if your model isn't working, it's not converging. If that's the case, usually your problem is that your model is misspecified. So you have to know how to diagnose your models in the same way that for traditional training an XGBoost model, you may have to learn how to check to see if your data is overfit For example, with these simulation-based MCMC dependent samplers, you're going to have to learn how to diagnose whenever your chains aren't converging and understand what that tells you about your data generation process. Do you have an inefficiently defined process, or is there some piece of information that is important that you've neglected to include? So it's a kind of long-winded answer to say that it depends, and it's why data science is an evolving field, and why it takes a bit of takes some training and experience to kind of get a feel for how things work.
Thank you for that.
Of course.
Does anyone else have any questions for Ben? Do you see that one, Ben? What ethical problems have you come across with your analysis?
Yeah, that's interesting. So I mostly work, where I'm going to go with this is I mostly work in financial markets, which with, open data, or it's not free, but publicly available data that you have access to if you pay for. Now, I haven't personally ran into issues like this, but I know some of my collaborators in the community, especially if you're working with like startups and smaller companies, you've got a lot. As you start to gather data to build models, you may gather, for example, like personally identifiable information, and you start to gather like some personal details, and you're able to make correlations and understand a little bit too much about the people that are included in your customer base. Even after anonymizing the data, you can still kind of make some correlations and figure out who's who in a way that people probably don't want you to do. And the challenge is that can be a profitable solution for people to do that. The onus is really on the researchers, really on the data scientists, and on the company to kind of act ethically and to not take advantage of that data, and to try and make sure that you scrub it when possible. And there's been a big shift in for example, like AI literature around reducing AI bias, and preventing like preventing the encryption of secrets in deep learning models. For example, there's an example of basically the deep learning models memorizing people's social insurance numbers in emails that were sent from whenever Google was building out its Gmail autocomplete tool. So yeah, the reality is that there's issues, and the onus is really on the people who are in the community, and for everybody to kind of speak up and to make their perspectives heard, that they're not, the engineers aren't willing to support, that kind of exploitative behavior.
Yeah, it's definitely everyone's responsibility. That's awesome. Does anybody else have another question? Feel free to turn on your mic if you want to make a comment, or if you have a question. I think we're good, Ben.
Awesome.
Yeah, thanks so much. That was really great.
Yeah, thanks everyone for attending. I really enjoyed it.
Sweet. So just wanted to say that we circled back to GDG Edmonton, and they opened up 10 more spots for the Python course. So I think they were